Thanks so much, everyone. I'd like to start by echoing all of the previous speakers and just saying how much fun this conference has been and how much I've learned throughout the conference. It's really been wonderful. And I'm particularly thankful for the opportunity to talk a little bit about some of my group's recent work on creating what I'd like to call something along the lines of a Landau theory for spin squeezing. And I'll try very, very carefully to sort of walk through what exactly that means as we go. But the essence of the talk is a very, very simple conjecture and a connection between metrologically useful entanglement in the particular form of spin squeezing and more standard statistical mechanical questions. And I hope to be able to convince you that in the end, at some level, we can think about there being sort of a paradigmatic phase diagram for whether or not a system spin squeezes, and that there's naturally associated transitions and a phase structure for that type of a scenario. So let me just start, even before providing a quick roadmap, by zooming out to 10,000 feet. This is something that David already mentioned in his talk, and sort of just orienting ourselves in terms of the next two talks of this particular session, which is that in terms of the lore, in some sense, for quantum metrology, the idea, of course, is that when one moves from a single particle sensor to a many-body sensor, from a purely classical correlation perspective, or really just thinking about statistics of the problem, one naturally expects to get a sensitivity improvement that goes as 1 over the square root of the number of sensors that one utilizes. And in this particular case, we usually think about this limit as the so-called standard quantum limit. Of course, we've already heard about this on Monday as well, but just want to make sure we're all on the same page. It turns out that the magic of quantum mechanics is that if one allows for quantum mechanical correlations and in particular entanglement between these different degrees of freedom, the sensitivity can improve, the scaling of the sensitivity can improve to being 1 over n, and this is the so-called Heisenberg limit for metrology. So I'd like to start with kind of a very, very simple question, which is that when we oftentimes in class learn about this notion of a Heisenberg metrology, a Heisenberg limit for metrology, we oftentimes learn about it in the context of a very specific set of different types of entangled states. So the common sort of classroom homework problem that we deal with is oftentimes working with the GHZ state and doing something like Ramsey spectroscopy. But of course, there's also examples of spin squeeze states, noon states, W states in certain contexts. But it turns out that whenever we speak about approaching a Heisenberg limit for quantum metrology, oftentimes we speak about a very limited set of states. And if you think about the broader structure of Hilbert space, that's quite surprising. In some sense, the view from the broader spectrum of Hilbert space is actually that there's really entangled states in most of Hilbert space. Most of Hilbert space is extremely entangled, even more so than necessarily the states that we're usually thinking about for metrologically useful entanglement. And so in that sense, those states that we usually work with and that we learn about are really a very, very small, almost vanishing subset of this type of Hilbert space. And the broader context of the question that I'd like to focus on today is whether or not, in some very broad sense, there can be fundamental guiding principles for helping us to figure out whether there are other states in this vast Hilbert space or whether there are other Hamiltonians that can also be useful generically for metrologically useful sensing. And it turns out I'd like to offer a very, very simple conjecture, and we'll sort of really unpack the conjecture in the talk today. And the conjecture is about a very specific form of entanglement, that of spin squeezing. And my claim is that spin squeezing, we'll see, has a very, very deep connection to a particular type of finite temperature magnetic order. And in particular, it's finite temperature magnetic order that ends up breaking a continuous symmetry. And we'll sort of unpack that as we go. So with that, let me give a very, very quick roadmap. I'll start off basically immediately writing down the class of Hamiltonians that will feature throughout the talk, but we'll sort of walk through each piece of the Hamiltonian. There was already beautiful stuff from James on Monday about spin squeezing, so I'll try to just give a little bit of a reminder about spin squeezing in the ideal one-axis twisting case so that we're just all on the same page again. Then I'll try to make a little bit of analogy by just looking at two pictures and trying to build an intuitive connection by mentioning these two pictures. And then I'll move on to describing the conjecture in more detail, how to think about spin squeezing as being equivalent to a finite temperature version of continuous symmetry breaking. And finally, I'd like to, in the Outlook, mention some recent experiments in collaboration with Antoine Brouwers's group on looking at this particular form of finite temperature magnetism. So let me start. The particular setting for this talk today is a setting that actually many of you have seen and are very familiar with. It's a particular strongly interacting spin model that's quite relevant to atomic quantum simulation platforms. The Hamiltonian looks like it has lots of terms in it. We'll unpack each of them. But I really want to emphasize at some level that thinking about this from the perspective of what types of spin Hamiltonians are sort of natural, in some sense, the class of Hamiltonians that I'm writing here is approximately the most natural one that one might expect. It's kind of the class that dipole-dipole interactions naturally fall into. So there's many different systems that really, fall under this particular class. And I don't need to emphasize that anymore. In fact, you just heard in the morning from Zoe's talk about this, an example of this particular class of Hamiltonian for a particular set of parameters. So the Hamiltonian that we're going to consider has two terms. It has an Ising type interaction with a coefficient Jz, and then it has an XY type interaction, which simply corresponds to spin exchange or flip-flop between two spin degrees of freedom that has an overall interaction strength J perpendicular. There's an overall minus sign in front of the Hamiltonian, which means that all other parameters in the Hamiltonian being positive, naturally we have spins wanting to align in the XY plane if J perpendicular is the largest energy scale, and naturally aligning in the Z direction if Jz is the largest energy scale. In addition, I'll also allow, for a little bit of genericness, to allow that the power law interaction between these spins to be variable with power law alpha. It's not the alpha that we've heard about in other contexts, and I apologize that somehow in the community we often use this alpha like this. So the context that we're going to be thinking about is really this particular Hamiltonian, consisting of n spin 1/2 on some sort of a lattice geometry. Could be in 1 dimension, 2 dimension, 3 dimension, but we're going to imagine it on some sort of a simple lattice geometry. And it turns out, as I was emphasizing, as we heard in Zoe's talk already earlier today, that really this Hamiltonian naturally emerges in a variety of contexts. It emerges in the context with Rydberg atom arrays. It emerges very naturally in the context of polar molecules. It emerges in the context of Hubbard models. But the specific parameter regime, both the dimensionality of the system as well as the ratio of the Ising to the spin exchange, certainly depends on the experiment. But as a general class, oh boy, sorry, we'll clean that up afterwards. As a general class, it turns out that this Hamiltonian really is a very natural starting point for thinking about spin models. So the question that I'd like to focus on for today's talk is actually extremely simple. It's, does this class of Hamiltonians lead to good spin squeezing? And I'll really unpack what we mean by good in a second, but in order to ask this question, we should start with a particular protocol, again, which we've heard about a little bit already on Monday, start with a particular protocol for doing spin squeezing in the first place. And the protocol is the most simplest one that we could imagine from a dynamics perspective. Throughout the talk, we'll imagine that the protocol that we have in question starts with a product state of all of the spins aligned in the x direction. And then we will simply time evolve with a particular Hamiltonian of interest, in this case H being written here. And the question that we'll ask is whether or not this Hamiltonian ends up being able to lead to good amounts of squeezing. In order to define what we mean by a good amount of squeezing, I want to harken back to James's talk, where we recall a little bit about the ideal case where this protocol does in fact work well. And that, of course, is the case of one-axis twisting. The one-axis twisting Hamiltonian corresponds to this all-to-all interacting Ising term. And of course, because it's an all-to-all interaction, we can rewrite this as sigma z total, the total spin operator in the z direction squared over n. And just again, give some intuition for sort of what squeezing looks like in this case, if we start with a quantum state, which is a product state aligned along the x direction, and we look at the projection noise in the yz plane, time evolution under this particular Hamiltonian naturally leads to a shearing. It leads to, in some sense, a z rotation that is sigma z dependent. And the shearing, of course, naturally leads to a change in the shape of the quantum spin projection noise. And this change in the shape of the quantum spin projection noise is precisely what allows one to improve the phase resolution of this particular state at intermediate times of evolution. And in this particular case, it turns out that we often refer to this one-axis twisting protocol as kind of the optimal protocol for spin squeezing, or as the optimal protocol for scalable spin squeezing. So let me define very precisely what that means for just a second. So what we mean when we ask the question of, does this particular protocol or does the particular Hamiltonian allow for a good amount of spin squeezing, is whether or not it allows for spin squeezing as good as this ideal case of one-axis twisting. And in the ideal case of one-axis twisting, it turns out the most natural way to characterize this type of spin squeezing, or the change in the shape of the projection noise, is to introduce a parameter called the spin squeezing parameter, represented as c squared over here. Basically just tells you about how the shape, what the shortest distance for the variance is in this yz plane. And it turns out that in the case of one-axis twisting, this all-to-all Ising interaction, the spin squeezing parameter scales as 1 over n to the 2/3. So as you increase the number of spins of the system, the spin squeezing parameter improves as 1 over n to the 2/3. And this is oftentimes in literature what we refer to as scalable amounts of spin squeezing, or the optimal scaling in this one-axis twisting case. It turns out that this scaling of the squeezing naturally leads to a sensitivity that's certainly better than standard quantum limit and almost as good as Heisenberg limited sensing, but not quite. In addition to the squeezing parameter improving as a function of increasing the number of spins, it turns out the optimal time of evolution at which we get the optimal amount of squeezing also increases as a function of n with a different power law, n to the 1/3. Just two characteristics of what we should think about when we talk about optimal spin squeezing and the scaling therein, as we'll come back to in a little bit. So let me rephrase the question that we started out with the talk, which is now, is it possible, or could this type of scalable spin squeezing, an optimal scaling like 1 over n to the 2/3, could this happen more generally for Hamiltonians that are, for example, not all-to-all coupled and do not look like the one-axis twisting Hamiltonian? And in particular, the question that we're going to ask is, for this class of Hamiltonians which naturally emerges in a large number of atomic quantum simulation platforms, is it possible, in fact, that we don't need to necessarily, although there's beautiful work doing this, engineer one-axis twisting, but simply time evolving with the natural Hamiltonian that you get from something like dipole-dipole interactions, you already get scalable spin squeezing? And here, I want to emphasize that when I really emphasize this generally over here, I really would like to restrict to situations that are short-ranged in some sense, where we really have a situation where the power law is larger than the dimensionality, so that we don't have Hamiltonians that are very naturally super extensive in nature. So before answering this question in a little bit of detail, let me start with a little bit of cold water. It turns out this question was already asked in the specific case very nicely of the Ising interaction. The question there was very simple. If we take this all-to-all Ising interaction and simply demote it to a power law Ising interaction, is it possible that one can still get scalable spin squeezing with a short-ranged, reasonable type Hamiltonian that you might find in the lab? It turns out the answer to this question is no. That the only way to actually get scalable spin squeezing in this purely Ising scenario is essentially all-to-all. You have a power law that has to be less than 2/3 times the dimensionality of the system, so it's really an ultra long-range interaction that naturally is super extensive in the first place. But it turns out, returning to this particular Hamiltonian that has both spin exchange and Ising interactions, it turns out that maybe things aren't so bad. And in particular, I'd like to highlight some really, really gorgeous work coming out of Anna Maria Ray and Jun's group, as well as Tommaso Roskilde's group. And it turns out that I'd like to make sort of a matching between two pictures to sort of start off explaining this idea of the conjecture. So it turns out what we're looking at here is a question related precisely to this Hamiltonian. And the question, for example, that's being asked here is, if you start with the product state, you don't ask yourself necessarily, is the squeezing scalable, or how does it scale extensively or not? You just ask yourself quantitatively, does it look like there's some amount of squeezing, or does it look like there's very minimal squeezing? So in the numerics here, you start with a state along the x direction, and you time evolve with this Hamiltonian. You look for the optimal amount of spin squeezing, and what the ray group is plotting here is that optimal amount of spin squeezing as a function of the parameters inside the Hamiltonian. There's both the power law on the y-axis over here, and the ratio of the Ising to the exchange interaction on the x-axis over here. And what you find is that in certain regions, it looks like quantitatively there's some amount of squeezing, and in other regions, it looks like there's not very much squeezing. And what I claim here is that this particular picture bears a remarkable amount of semblance to another picture that one can make for the same exact Hamiltonian, but that's very different in nature. And in particular, you can also ask for this Hamiltonian, what is the zero temperature ground state phase diagram of this particular model? And here, it's a beautiful paper by Ferromagnet et al. On the y, and I claim that sort of these two, bear a remarkable resemblance. It's hard to kind of see this resemblance because you have 1 over alpha over here, and it turns out jz over jperp is a little bit flipped. So using the magic of PowerPoint, let me help you a little bit. So it turns out you can now see that, okay, somehow it looks like maybe there's some structure here that bears resemblance for the ground state zero temperature phase diagram of the model, as well as a totally different dynamical entanglement question, which is there spin squeezing? And the conjecture that I'd like to offer both zooms out a little bit and generalizes this picturology, this comparison between these two pictures. And in particular, the conjecture is the following, that whenever you have finite temperature, continuous symmetry breaking, so this is the same as this XY magnetic phase, but no longer at zero temperature, I want to elevate the requirement to there being stable order of an XY form, but at finite temperature. My claim is that whenever there is finite temperature continuous symmetry breaking, that there naturally you get scalable spin squeezing. And what I mean by scalable spin squeezing is that it scales as good as the case of one-axis twisting. So c squared, for example, scales as 1 over n to the 2/3. The optimal time, for example, should scale as n to the 1/3. But you should look at this, and already you should feel a little bit surprised. In some sense, the two sides of this conjecture are extremely different from one another. On one side of the conjecture is a finite time dynamics question about how much metrologically useful entanglement is generated as a function of time evolution from a product state. It's characterized by the so-called spin squeezing parameter that we introduced. On the other side of the equation is sort of a classic question, in AMO and condensed matter from the context of finite temperature stat mech, but it's a very, very different question. It's sort of an equilibrium question about the phase diagram of that same Hamiltonian, but asking in a different context. And of course, the characterization of this particular right side of this is very different than the spin squeezing parameter. It's really characterized by the order parameter associated with the order. And here, again, we're really going to be interested, I claim, in the case where you have to have continuous symmetry breaking. So an Ising magnet that breaks just the z rotational symmetry is not going to be sufficient for spin squeezing. You must break a continuous symmetry, so you need to get an easy plane or an XY type magnet. So let me try to start building a bridge for us. It's, again, very, very simple. Let me try to start building a bridge for us. How do we actually build a bridge between these two? Well, the most natural starting point might be, let's try to introduce a notion of temperature into the spin squeezing protocol in the first place, right? Because we just started with a product state there and evolved. The notion of temperature that we introduce is kind of the most obvious and the most standard way to introduce this notion of temperature, but let me do it carefully. So we emphasized that for the spin squeezing protocol, we started out with a product state. And to introduce this notion of temperature, I want us to measure the energy density of this product state with respect to the Hamiltonian that it will ultimately be evolving under. Once we get the expectation value of the energy over here, we divide by the system size. And of course, that gives us the energy density associated with the starting state in that particular Hamiltonian. To build a connection to a temperature, you look at the same Hamiltonian, but you look at the Gibbs states of this Hamiltonian at an inverse temperature 1 over beta. And you also compute for these Gibbs states the same energy density. And of course, what we all learn in sort of standard stat mech is that the definition of temperature for an initial pure state, for example, is when you match these two energy densities, then we can define a well-defined notion of temperature for that initial starting state. So let me further refine the conjecture one more time. With this definition of a temperature, the conjecture is the following and includes 2 steps. My claim is that if you have a Hamiltonian, and if that Hamiltonian supports finite temperature, continuous symmetry breaking order, there's a lot of words here, but it's really very simple. It's just if there is ferromagnetic order in the easy plane direction, but it has to be at a finite Tc. If the Hamiltonian supports this finite temperature xy order and your initial state is at a lower temperature than the critical temperature associated with that order, you must squeeze. That you will, in fact, always, under dynamics from product state of this type of a Hamiltonian, get to optimal scalable spin squeezing. Let me try to test this conjecture a little bit together with you. And let me start with, again, looking at the 2 sides of the conjecture, just to build some sense of what exactly it looks like to order and not order, and what exactly it looks like to spin squeeze and not spin squeeze. So let's start with the ordering side of the transition. And in particular, if we start with the state aligned along the x direction, we can ask about order in a very simple way. We time evolve under this particular Hamiltonian, and we simply measure the xy magnetization, the order parameter for this particular type of an easy plane magnet. And in certain parameter regimes, we're looking at a 2-dimensional square lattice of spins in this case, with a particular power law and a particular value of jz over jperp. Jperp is said to be unity over here. You find that if you look at the expectation value of the xy magnetization, this is increasing system size as darker colors, you find that it naturally, in certain parameter regimes, will plateau. And whenever you have a plateau like this, you're used to thinking about this as being in the ordered phase of that particular Hamiltonian, that you plateau to a particular value of the order parameter. At other points in the phase diagram, for the same exact Hamiltonian, but just changing the parameters, you find that as a function of system size, the magnetization, or the amount of order, the order parameter goes to 0, and in this case, we would say that's an example of a situation which is disordered. Keeping the same parameters exactly for these 2 plots, let me now ask the exact same question for what does squeezing look like in this context. So here, again, we start with the same initial product state, we time evolve, and then we measure the spin squeezing parameter as a function of time. And let me just remind you that the definition of optimal scalable spin squeezing is that c squared, the squeezing parameter, improves as 1 over n to the 2/3, so it should get smaller as a function of increasing system size, and the optimal time at which it approaches its best value should increase as a function of system size. And for the right set of parameters that we had over here, this is precisely what you see. As a function of increasing system size, lighter to darker curves, you see that the location of the minimum in time of the spin squeezing parameter optimum shifts to the right, gets the larger times as you increase system size, and gets to lower values. And you can collapse this perfectly using a 1 over n to the 2/3 scaling. So you really find that, at least in this particular setting, it looks like one has scalable spin squeezing. On the other hand, in the case where one often finds that one has a disordered system, so it's a paramagnet instead of being the XY regime, it turns out that the spin squeezing behavior looks extremely different. It now doesn't change in time as a function of system size, nor does the spin squeezing get better as a function of system size. So let's try to generalize this a little bit by looking at the entire phase space of the allowed parameters of the Hamiltonian. So we just said in the ordering case, we have in examples where order is plateau, disorder is no plateau. In the spin squeezing case, we look to see whether the spin squeezing improves as n to the 2/3 or whether it does not improve as n to the 2/3. And instead of asking it for a particular point in parameter space, we can of course ask it for multiple points in parameter space throughout this sort of alpha and jz phase space. And what we find, this is now in dimension d equals 1, is we find that when we characterize it precisely as asking the question of, does the spin squeezing that's generated look like it scales in a scalable fashion, we find a pretty reasonable bright line that separates between what I would call kind of a non-squeezing region of the phase space and a scalable squeezing region of the phase space. We can ask, again, a totally distinct question. These two are sort of really unrelated questions at some level. A totally distinct question is whether or not that initial state is below the critical temperature, if there is one, of order in the particular Hamiltonian at the particular point in parameter space for a given alpha jz. And in this case, we find that that initial state will be in the XY magnetic phase in this region of the phase space, and in the disordered paramagnetic phase in that region of the phase space. And it turns out, when you put these two together, it indeed looks like they overlap quite well, so that wherever you have spin squeezing, you really have that corresponding to the situation where you have the initial state being at low temperatures relative to the finite temperature ordering of an XY magnet, and whenever you don't have this, it looks like you're in this sort of non-squeezing phase. This is true in both dimension d equals 1 and dimension d equals 2, although the phase space looks quite different in the two cases. And I should emphasize that there is a beautiful microscopic intuition for what the actual connection between this stat-Mecke question and what the spin squeezing question is, and it's really related to the low-energy eigenstructure of continuous symmetry breaking and how that eigenstructure actually looks extremely reminiscent of one-axis twisting in the first place. But it turns out that there are also some extremely subtle open questions about the nature of the scaling at long times and at large system sizes that I think are more or less impossible to answer analytically or numerically, and there I think that experiments will be really important. In the last just 2 minutes, I wanted to turn over to experiments for just a quick second in the outlook and mention that, in fact, for example, there are a number of platforms that I've already alluded to which are quite natural in terms of sitting at interesting regions in this phase space. The specific one we'll focus on today is actually an experiment in the Brouwers group. I should mention that Guillaume Bornet had a poster yesterday, but still around, so if you want to find him, you can talk, and Daniel Barreda, who's also an expert on the experiment, is around as well. So let me just finish with a little bit of experimental progress towards this direction. And in particular, let me start with a following recollection, which is that, in fact, in a two-dimensional system, if you have nearest neighbor interactions, there can never be any finite temperature continuous symmetry breaking from Merman-Wagner theorem. So the first question that's natural to ask, for example, is if you have, for example, a long-range XY-like model, as exists in Antoine's experiment, is there a finite temperature XY ferromagnet in the first place? Is TC non-zero? Because if you have TC being 0, then you can never get spin squeezing scalably in the first place. And it turns out the way they explore this question is by literally trying to prepare this finite temperature XY ferromagnet, but starting from a Néel state in the Z direction. So they turn on a very strong staggered magnetic field. This is a Rydberg tweezer array 10 by 10 on a two-dimensional square lattice. They turn on this site-dependent AC Stark shift that leads to a large staggered magnetic field, and they align the spins so that we're effectively at very low temperature relative to this Hamiltonian. And then what they do is they adiabatically ramp down this staggered magnetic field and try to prepare the XY ferromagnet and then to measure the long-distance correlations of that XY ferromagnet. And indeed, what they find is honestly quite beautiful to me. When they look at these XX correlation functions, here's a real space picture of it as a function of distance. But if you look at these XX correlation functions as a function of averaging over spins at a given distance, it really looks like it does plateau to a finite value consistent with there being an order. I should emphasize that this isn't just what you always get. If you turn the sign of the Hamiltonian so that you have an anti-ferromagnetic XY term, there you expect only algebraic long-range order, and in fact you do see the XX correlations look like they decay quite well to 0. So ultimately they're able to map out kind of a phase diagram for this finite temperature XY ferromagnet as a function of the strength of the staggered magnetic field, sort of a quantum tuning parameter, and as a function of a proxy for the effective spin temperature of their system. And I should just emphasize that, sitting in this region, I think, is a particularly interesting place to be, and that time evolution from just a trivial product X state should be able, in principle, to give us scalable spin squeezing in this region. Let me end by acknowledging the people who did the work. This has really been a wonderful collaboration across lots of disciplines. On the spin squeezing side of things, it was really led by Max, Bingtian, and Emily, who are students, and Emily and Brendan, who are postdocs. And it's been a deep collaboration with Bert Halperin. And on the experimental side, of course, it's been a super fun collaboration with the Brouwys group. On the theory side, it's been Marcus, Vincent, Shubayu, and Johannes, and a really fun collaboration with my colleague Mike Zalatel at Berkeley. And let me thank you for your attention.
Thank you for a very fascinating talk. We have time for questions.
Sorry.
Yeah, so it's a multiple-fold question. So it's super interesting. My first one is, why do you have those scaling constraints on n to the 2/3, etc.? Because it sounds to be like really interesting to compare those two cases of this phase diagram and this like dynamical evolution, but like in some sense they look so good together. If you told me, oh, I don't have the same scaling, I wouldn't have cared that much. But I have the impression you do care about having the same scaling, so I'm wondering why. The other thing is, in my head I was trying to find another example of a system that has this sort of analogy between its ground state phase diagram and dynamical evolution of an excited state, and I just couldn't find any simple example. So if you have one, and from that question, like, if you don't have one, how do you get the idea of looking at that and comparing those two things more on a like research perspective? Like, why do you have the intuition of looking at this?
All three super good questions. Let me answer them one by one. Actually, they're actually really good questions. So the first question was, is it important, or why does one impose or talk about this, scalable spin squeezing? So it turns out there's maybe two answers to that question. The first answer is that, the comparison, one can naturally ask a question which is, just is there some squeezing in the first place? And maybe, there's squeezing for, certain system sizes, but at some point the scaling sort of no longer improves as a function of system size, and then one reaches some sort of a plateau in that behavior. Still super interesting and useful from a pragmatic perspective, but a little bit different in spirit from trying to ask whether or not one gets this optimal scaling. But the maybe slightly more honest answer is that, in fact, we weren't necessarily expecting that in this region where we see squeezing, that you always get optimal scaling. And it could actually be, and we're not sure, that's sort of the subtlety of one of the questions that we're wondering about. It's not exactly clear to us as you approach this phase boundary whether it could be the situation that the scaling with the spin squeezing is still better than SQL, but not as good as 1 over n to the 2/3. So you can imagine some continuous change where 2/3 at very, very deep in the phase diagram then maybe gets to something like 2/5 or 3/5 as you approach the phase transition, and ultimately at the transition it then goes to SQL. We can't rule that out, but for very, very large system sizes, at least as far as we can get to in kind of semi-classical numerics, it really looks like for a large system size that this n to the 2/3 scaling holds. But there is no fundamental reason that there can't be sort of a change in the scaling as you approach that. The second question is this analogy more broad in some sense than just, this example over here? And the answer is yes, but it's again subtle. So it turns out that if you think about the time evolution of pure states, or pure states in general, and you ask about the quantum Fisher information of the pure state, which is its metrological usefulness for sensing a particular parameter, it turns out that when you write down the quantum Fisher information, if you give it to someone who's used to looking at StatMech, it literally looks like the definition of a long-range correlation function or an order parameter. So in that sense, there is a very, very deep connection between symmetry breaking and, for example, quantum Fisher information or metrological usefulness in the first place. But it's extremely subtle. So the example there, the classic example, is actually that if you have an Ising ferromagnet and you think about the cat state of that, it's the GHZ state. So again, there's a very natural notion between discrete symmetry breaking and that type of a GHZ state. But it turns out, very generically, if you want to make use of the symmetry breaking to quantum Fisher information connection, you need to wait for time evolution until the system thermalizes. And once the system thermalizes, it's extremely difficult to read out that metrologically usefully enhanced measurement in some way. The advantage in the spin squeezing case over here, something I didn't emphasize, is actually that you get this connection already at extremely short time scales. You don't wait until the system fully thermalizes. You already sort of get optimal scaling before that actually happens. I hope that answered all three questions.
Yeah.
So since I already have a mic in my hand, I can't resist a quick follow-up. It might be naive, but you keep using the term optimal scaling to mean this n to the 2/3, whereas I would have thought you might just compare with the Heisenberg 1/n. So is it just obvious that for this class of Hamiltonians, you could never beat what you're calling optimal?
Yeah, it's a super good question. I don't think there's any proof one way or the other, but I should be super clear that if you just think about one-axis twisting to start off, of course, from the spin squeezing question, the optimal scaling is 1/2/3, but at some point, if you allow for the evolution to keep going further, you get a Dickey state, which can be Heisenberg limited. So it's really zooming into the specific question about spin squeezing and the observable that we think about this 1/n to 2/3. There's no proof, I think, that you can't have, one of these types of a class of Hamiltonian that does better than n to 2/3, but it's very hard for me to imagine asking about spin squeezing that it does better than one-axis twisting. So that's sort of, what I mean when I say optimal.
Time for another question. There was one off on that side over there.
Yes, I have probably 1.5 questions. The first one is about excited state quantum phase transitions. Do you know whether this class of Hamiltonians exhibits excited state quantum phase transitions? And if yes, do you know whether the connection that you make between squeezing and thermal phase transitions holds also as a connection between squeezing and excited state quantum phase transitions?
Okay, super interesting question. I'll try to answer it, but if I don't, I'm happy to chat afterwards. So when we talk about excited state quantum phase transitions, I'm not exactly sure I know precisely what you mean, but let me try to interpret it in this language for a second. At t = 0, we can talk about ground state quantum phase transitions or phase transitions in general. And whenever we go to the excited state, I think about usually there being a finite temperature or a finite energy density. So we've somehow moved ourselves into this finite T regime. And then basically, if you ask about an excited state quantum phase transition, I would imagine sitting at a finite temperature and then tuning another parameter, basically, that can tune a transition again from the XY ferromagnet to the paramagnet. And in fact, in this model, that's exactly what's expected to happen. So you expect that at finite energy density, if you did a tuning parameter like the staggered magnetic field that Antoine's group is working with, you do expect that there is I still think about it as kind of a classically phase transition, but it is done via sort of a tuning parameter that's not temperature. Whether or not the dynamics associated with that look quantum or classical depend on whether or not we're in this quantum classical fan region or not. But I think that, at least in terms of the existence of that type of phase transition, that certainly exists in this case.
Yes, I have the impression that, so in finite size systems, the excited state quantum phase transitions are defined by looking at the eigenstates, energy eigenstates of the Hamiltonian and tuning the Hamiltonian parameters. But of course, if you go into the infinite size limit, which you have to do if you talk about phase transitions, then the notion of eigenstates becomes less clear or unclear or not well defined, and then it becomes the energy density, which is on your second axis. And because your effective temperature is defined by using the energy density, I have the impression that I would expect that you get the same connection with the excited state quantum phase diagram.
Yeah, maybe let me zoom out one more second and try to make that statement precise a little bit more. In some sense, here, I guess, the connection between sort of eigenstates and what we're looking at is, there is a connection, but sort of a little bit distinct in the sense that, we're always imagining evolving some pure state. So I never sort of want to necessarily ask about the eigenstructure, but it is actually, in fact, the structure of the excited state eigenstates and the energy differences between them that ends up leading to what actually looks like spin squeezing in the first place.
Yes, and thank you. And the other half question...
I'm afraid I think we're going to have to cut it off there. I apologize. I know there are many other questions, but in the interest of time, let us thank Norm one more time for that wonderful talk.